Okay, so this is going to be the types of reactions I expect you to know. So the types of reactions I'm going to expect you to know are uh, for the alkanes. You should know halogenation. And halogenation is when you take something like CH4 and you add a halogen to it. And for this reaction, you need light. What happens is one of the hydrogens gets taken off of your alkane and replaced with the bromine. The other bromine combines with the hydrogen that's taken off and you get HBr. This would also happen with Cl2, F2, I2, but it's mostly done with bromine and chlorine.
And is this the one that you can keep taking or keep adding H's?
Right. If we did this, we would get this. Oops, this should be a 4. So all 4 get replaced.
Okay.
So if we did something like this, and where we ask for all dibromo products, you would get this. Plus that. Plus that. Plus that. And plus that, you get 1, 2, 3, 4, 5 products. Oops, 4 products.
Okay, and
I have 2 of them down. They're the same.
is this CH3Br, CH2Br2, CH4Br3, and CBr4?
This one here would be CHBr2, CH2, CH3.
Okay,
then,
so when you go through all of them and remove each hydrogen, the ones that you're drawing aren't those 4 products that I get then?
No, I'm asking for all the dibromo products. So that means only 2 hydrogens are gone.
Oh, okay.
So that's the key here, dibromo. And, you could ask for all the tribromo products too. Tribromo, you'd have to put 3 bromines on there.
Okay.
So
So
you
that
see,
means
with my solutions, what I did is I put both bromines on the first carbon, both on the second carbon, then one on the first, one on the second, one on the first, one on the third, and that's all the possibilities. So that's a reaction you should know. You should also know combustion. Combustion is a redox reaction. And you basically take something like this, you react it with oxygen, and you get CO2 and H2O. And in this case, we put a 2 here, and we put a 2 here, and that should be balanced. So this one requires light. And the interesting thing about this is these solutions are brown. But this product is not brown. So if you put these together with the light on, what you'll notice is when you put these together, it's kind of like since this is a colorless solution and this is a colored solution, when you mix them together, it becomes like a light brown. But over time, guess what happens to the color?
becomes clear.
Yeah, the color disappears. Now, guess what happens if you don't have light around?
No reaction.
The color stays light brown.
Okay.
Okay. Now, here are the reactions for alkenes that you should know. You should know halogenation. You should know hydrogenation. You should know hydration. What else should you know? You should know, that's pretty much it for those. You should also know combustion. So halogenation works like this. So here, it doesn't matter whether this is cis or trans. I just want to put the double bond in the middle there. If you react this with Cl2, what will happen is this.
Right.
Okay, and you don't need light. So this is a great way to tell the difference between an alkene and an alkane. You put it together, you put each of them together with bromine, or let's say you have an unknown and you don't know if it's an alkane or an alkene. So you add a little bit of bromine to it and you keep it in the dark. If it stays brown, what does that mean? Alkane. If the color disappears, even though it's dark, that means the bromine is reacting. You have an alkene.
Okay.
You kind of follow? So if you have an alkane plus bromine, this is going to be light brown.
And you need light for that reaction.
And here, if you have no light, it stays light brown.
Right.
So what does that mean about this stuff? Is it reacting or not?
It's not reacting if it stays.
Okay. If you take an alkene and bromine, this is light brown. And here, no light, it turns colorless because the bromine reacts. So if you have something that you don't know if it's an alkane or an alkene, add a little bromine, leave it in the dark for a little while. If it turns colorless, what does it mean?
That it's an alkene.
Right. And if it stays light brown, what does it mean?
It's an alkane.
There you go.
Because alkenes don't need light for the reaction?
That's right.
Okay.
Okay. Hydrogenation is this. So what's happened here? Do you see how this carbon has one hydrogen on it?
Yeah.
You see how the same carbon now has two?
Right, on both ends of the bond.
And here, this only had one, now it has two. Well, how come these now have two hydrogens on them instead of one each?
Because we added
one hydrogen added to one added to the other.
Okay.
And hydration is simply this. OH adds to one hydrogen and hydrogen adds to the other carbon. I should say OH adds to one carbon. Now with hydrogen, with hydration, it does matter sometimes it matters which one you put the OH on. Because if we had this, these would be your products. But here we would have this. We'd have both of these. Do you see how these two are different?
Carbon 2 and carbon 3?
Yeah, this one would be called 2-pentanol, and this one would be called 3-pentanol. But the point is that the OH could add to this carbon here or to this one here.
To either side of the bond.
Yeah. And then combustion, of course, what's going to happen?
Plus O2.
And what do you get?
CO2, H2O.
There you go. So you should know these reactions with alkanes, plus one more. The other one is polymerization. So in polymerization, what happens is, let's say that this is your alkene, okay? So I'm just going to put A, B, C, D. These could be hydrogens. They could be CH3s. They could be chlorines. They could be fluorines. They could be a number of different things. You with me?
Right.
So here, plus you add some initiator. And this is what you get. So this is the repeating unit. And you know it's a repeating unit because you see this bond here that goes outside the parentheses?
Yeah.
That connects to the preceding unit. You see this one that goes outside the parentheses?
Yeah.
That connects to the next unit. What does the next unit look like? It looks exactly like that.
Right.
So this is how we make things like polystyrene, polyvinyl chloride, the plastics that you have in your soda bottles. It's how we make the coating for glass that keeps it from shattering when you drive a car and you get into an accident. It just kind of spiders. So it's also responsible for plexiglass. This polymerization reaction is used in a whole lot of plastics.
So
go ahead.
Sorry, what was the initiator again? Was it, I forgot.
The initiator is just a free radical. You don't need to know what this is. It's just a molecule that usually responds to light and it makes a free radical.
But then it like catalyzes the bonds, changing to single bonds.
Yeah, so this is a common initiator.
And the initiator will be on either end, right?
Right. So this is a common initiator, and this bond breaks, and what you end up with is a single electron and a single electron here.
Okay.
So the initial is what we call a free radical. And free radicals are called free radicals because they tend to react with anything they run into. And the only way to stop a free radical is with another free radical.
Okay.
But this you don't need to know about. And have you ever heard of that this water bottle is bisphenol free?
Yeah, the BPA.
Yeah,
polyphenol or whatever.
Yeah. So the reason they talk about that is because the initiator is that stuff. And so they're not using that as an initiator. They're doing something else.
The initiator is the BPA, and that's supposed to be bad for you?
Yes, absolutely. Well, it's a free radical, right?
Yeah.
It turns into a free radical. So yeah, hell yeah, it's bad for you.
Sounds pretty bad.
So they're doing the polymerization some other way, but they're still doing the polymerization.
Okay.
So you should know that for alkenes. You should also know hydrolysis and condensation. Condensation. So condensation is when you take a carboxylic acid and an alcohol, and you make an ester and water. Now, condensation really means to put together, but I kind of remember this reaction because it makes water, and I think of condensation being like water. So if you take a carboxylic acid, and here it doesn't matter what this is, so I'm just going to make this a smiley face, because it can be whatever you want over there, and an alcohol, Now you'll notice with the alcohol, I'm showing this bond here. And for the alcohol, this can be whatever you want. So I'm just going to put we'll make it an unhappy face so that you don't have to think they have to be the same. What happens here? Let's see. What happens here is this OH and this H combine to make water. And this piece here that's left over, and this piece here that's left over combine to make the ester. So this is your acid, this is your alcohol, and this is your ester. And this is called condensation. Okay. Now let's look at hydrolysis. So I'm going to take my smiley face and my unhappy face. And now I'm going to add water. And usually this takes a catalyst of sodium hydroxide. And this is a catalyst. It's not used in the reaction, but it does make the reaction go faster. And I'm not sure if I described this to you before, but an analogy of a catalyst is a spoon when you're eating cereal.
Okay.
A spoon really helps when you eat cereal, doesn't it?
Well, yeah.
Yeah.
More efficient at eating cereal, I guess.
Yeah, otherwise you got to stick your face in there and go, it's like dunking for apples.
Mm-hmm.
Can you use the spoon again when you're done?
Over and over until you're done.
So a spoon is a catalyst for eating cereal. And the only reason dogs don't use them is because they don't have an opposable thumb. Okay, there's probably more reasons than that. So what's going to happen here is this is going to split right here, just like this bond was made right there. And you're going to add the OH back to that carbon. And you're going to add the H back to that oxygen. You see that this reaction instead of the one above?
They're kind of opposite.
They're not kind of, they are opposite.
Right.
Here, you make an ester and water. Here, you have an ester
and water that makes
and water, and you make an acid and an alcohol.
Okay, so they're like reverse reactions?
Yeah, they're the reverse of each other. So hydrolysis and condensation are opposites. Now there's another hydrolysis and condensation that you want to know. And that's this. So imagine, if you will, that you have this. Oops, my bad. Got to start over. So this, I'm not going to use a smiley face. I'm going to use a CH3 here. And do you see how this is a carboxylic acid?
A double bond and OH, yeah.
Okay, and now we're going to do this. I'm going to put an H here, and here I'm going to put a CH2CH3 and a CH2CH3 down here.
So you have two ethyls.
Yeah, so this is diethylamine.
Diethylamine, okay. The H and the N.
So what's going to happen here is the same thing as we saw before. You see this OH, it's going to come off and combine with that H. And what are they going to make?
An S.
Oh wait, no, OH and H.
water.
Right. So this is condensation also. Now you can see that the nitrogen is going to attach to this carbon. So this is called an amide. So the difference between this reaction and this reaction is that you don't start with an alcohol, you start with an amine. You don't make an ester, you make an amide. But it's still putting two things together and condensing them. So guess what happens if we take this add water to it and a little bit of sodium hydroxide.
You're gonna get an amine and a carboxylic acid.
That's right. Okay. So what's really neat about these reactions is that there's another polymerization reaction you should know. So let's see, I need a little more paper. I'm going to get up from my seat and grab some more. Actually, I can use the backs of these. So let me show you another polymerization reaction. And this is a condensation. So here you use a diacid and a diol to get your polymer, plus water. So I'm going to show you a very simple diacid.
So is that an acid and an alcohol then?
Yeah, but a diacid, so two.
And 2 is where there's two acid groups on it?
Do you see that's an acid?
Uh-huh.
Do you see that's an acid?
Exactly, okay.
Diacid. So here's my very simple diol. I'm going to put CH2CH2. Now, I'm going to put my arrow down here, and I'm going to start with this guy here, okay?
Okay.
So this OH comes off and that H comes off, and we get water, right? But we have to put in the alcohol. So there's the alcohol, right?
Right.
But I'm going to say that hydrogen comes off and that OH comes off, and then we add an acid here. And now I'm going to say, well, you know what? Of my new acid, that OH comes off and we add an alcohol. And then I'm going to say that H comes off and we add an acid. So when does this stop? And the answer is it doesn't. It goes on forever.
Okay.
So how do you draw the polymer? And the answer is what you do is you take the acid and you take the alcohol and the acid, you take the OHs off. So do you see I've taken the OHs off?
Right.
The alcohol, you take these hydrogens off. Do you see that here? You bond these together, and really what's happening is if you have N of these and N of these, you'll end up with N repeating units, and this is a polyester. Now, do you know what polyesters are found in?
Fabric.
Fabric, tennis shoes, all sorts of different things, right? Polyester
Synthetic
is
rubber.
responsible for, it's the greatest invention in mankind. Some people say it's the automobile. No, it's polyester. I mean, with the advent of polyester, I mean, you got to imagine, maybe you have to talk to grandma and grandpa about this, but the clothes they wore were kind of dull. Earth tones, because dyes weren't vibrant and fabric would not hold those types of dyes, right?
Mm-hmm.
But with the advent of polyester, you can make this stuff and you can throw dye in there and the dye molecules get caught into the weave, if you will, and you can get these really brightly colored threads. And with these brightly colored threads, you can make brightly colored clothes. And just, where would disco be without those bright colored shirts and dresses that people wore?
Right.
So clearly the greatest invention in mankind, polyester.
Dangerous too, though. It melts, doesn't it?
It does melt. Sometimes beauty has its risks. At any rate, that's a polyester. Now, it turns out that you can also do this with a dye acid and a diamine. So let me give you a different example here. So here's my diacid. And in between here, I'm going to put an aromatic ring like this. And for my amine, I'm going to put, let's see, what do I want to do here? H, and then I'm going to put NH, and then I'll also put an aromatic ring in here. So here, how do you draw the polyamide? Well, you do the same thing. What do we do with the acid to draw the amide?
We took the OH off.
That's right. And so we're going to do the same thing. So there's the polyamide from the acid. What are we going to do with our diamine?
We took the H's off.
Right. And here's your polyamide. Polyamides are very common also. Have you ever heard of a substance called nylon?
Yeah.
It's criminals use it when they're robbing stores. They put it over their faces and it kind of masks what they look like.
Yeah.
Okay. At least that's what it seems that people use it for when I watch TV.
Well, didn't they use nylon a lot in World War II in like the aviation stuff?
Oh, sure. But I'm just talking about recently,
Well, stockings are always nylon.
Stockings too. Okay, so polyamides are, nylon is a polyamide. And there's something called 6,6 nylon. And what it is it's this. And this is the stuff found in stockings. So here, do you see how there's 1, 2, 3, 4, 5, 6 carbons in the diacid?
Right.
6 carbons in the diamine?
Yeah.
So that is 6,6 nylon, which is the stuff found in stockings.
Okay.
I'm going to write this a little bit differently. One, 2, 3, 4. So here's 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. So this is 6,6 nylon. And usually I do a demonstration in class where I have this solution that has this stuff in it. And it has this stuff in it, and both look like water, right?
Mm-hmm.
And I mix the two together, and then I take a little wire and I put it through there, and I start pulling out a string that looks kind of like snot, but I can pull the string out and keep pulling and pulling and pulling and pulling from what looks like a clear solution. And I've got this thread that I can pull and make it 6 foot long. I'm only limited by my height.
But is there water left over too, like in the other?
Oh yeah,
reactions?
absolutely.
So when we do the polymerization with condensation, should we always add water at the end?
Yeah, but it's not the major product that we're seeking or trying to figure out. It's really a byproduct.
Okay.
It does not become part of the string, as it were. So you can imagine, you know, the great talk around town when sheep found out that we had discovered polyester and polyamides. They were thinking, oh my God, we're going to be out of a job.
They're going to forget.
Yeah, what people need to wear wool. So, but it all worked out. I'm sure they're happy now. All right, so those are the types of reactions that you should know. Off the top of my head, I can't think of any other reactions that I really want you to know. The book does talk about some reactions of alcohols, and I don't think those are as important for us right now because they're a little more difficult. And you'll cover those in organic chemistry when you take organic chemistry. But the ones with alkanes are pretty easy to recognize. The ones with alkenes are pretty easy to recognize. And condensation reactions are, you know, of huge importance in the world these days. I mean, you can't walk into a home without seeing a condensation product or an addition. I should say you can't walk into a home without seeing a polymer.
Because it's just most plastics.
And the thing about polymerization, the thing about polymerization is that it also occurs naturally. You're made out of polymers,
right?
And those polymers are called proteins. Proteins are amino
acids.
Yeah, proteins are polymers where you actually have an acid on one side and an amine on the other side, and it reacts with an acid and an amine, and these two combine and make an amide. These two combine and make an amide. So your proteins are made of polyamides.
Mm-hmm.
So these are natural products. So polymerization reactions are of huge importance. And can you think of one other place where there's probably a polymerization reaction going on?
I don't know, you tell me. I don't want to be wrong.
DNA.
Okay, that's what I was gonna guess.
Well, DNA is a phosphate polymer.
Right.
So it's similar to these types of polymers, but it's got a phosphoester bond. So polymers are of huge importance to organisms naturally, without all the plastics and without all the fabric. So that's why we talk about these polymerization reactions. They're just hugely important.
Mm-hmm.
I will say that there aren't too many addition polymers naturally. So those are the ones that make plastics like a polyvinyl chloride, styrene, polystyrene, styrofoam, as it were, and so forth. Those don't occur too much naturally. All righty. So I don't know, does that help you with some of those reactions?
It does, yeah.
So why don't we take a look at the homework? And there are some things in the homework where I ask you questions about how do you do this and how do you do that? And they're actual reactions, okay?
Okay.
I need to get some more paper. I'll be right back. Okay, so I'm going to do a new share here. And I'm going to try and open up the homework if I can. There we go. So can you see the homework?
Yeah.
Okay, I'm making a few adjustments here. I muted myself, probably better for you.
I can still.
Okay. So let's take a look at some of these questions here. Number 1, 7 reasons for the diversity of carbon compounds. Do you know what 7 reasons are?
They're tetravalent. They can make single, double, or triple bonds.
Okay, I'm going to try and capture this now. So we're looking at the diversity of carbon.
Right.
Tetravalent. What else can we say about carbon?
It can make single, double, or triple bonds.
Single, double, or triple bonds.
It can be linear, trigonal planar, and tetrahedral.
Right.
It can form chains.
Yes.
It can be gas, liquid, and solid.
Right, at room temperature, which is hugely important.
They can be polar or non-polar.
Right, we have polar and non-polar. How about something related to chains? Branches. It doesn't have to be carbon, 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 carbon. It can be carbon, carbon, and then that carbon splits into 3 carbons, right?
Right.
So that's hugely important. Another reason, which seems odd for why there's so many different carbon compounds, is that organisms make them. And when you got 20 million species, you expect to have a whole lot of different organic compounds, right?
Right.
Okay, so we were going for 7, right?
Mm-hmm.
We got 8. Carbon easily bonds to
non-metals.
Other non-metals, which is what we expect in organic compounds, which are molecular compounds. Okay, so that's a pretty good list. We got what? 1, 2, 3, 4, 5, 6, 7, 8, 9. And we might be able to add 1 or 2 here later, but let's see. Oh, carbon has Goldilocks bonds. And this is probably more of a question where why is carbon so important to life? It's got the Goldilocks bonds. Now, what does that mean?
Not too strong, not too weak.
Right. Just right. Because if they were too strong, organisms would be made out of rocks that would never change. And if they were too weak, there would never be enough structure to make an organism. You with me?
Yeah.
Okay. Let's go to.
Could one other reason for that be the isomers, or could that?
Oh, that's an excellent one. But isomers is kind of tied into chains and branches, but still it's a good one because you have geometric isomers, right?
Right.
Cis trans and that kind of stuff.
Yeah.
So yeah, there's plenty of reasons to go around. Okay, let's look at number 2. Number 2 says for the following drawings, give the Lewis structure, structural formula, condensed formula, and molecular formula. So let's take a look at one of them. So here's the line drawing. What would the Lewis on this one look like? Well, you want to take each one of these and put carbons where they are supposed to be. So do you see I've placed carbons where they're supposed to be?
Right.
Do you also see that I have not put the H2s here?
Mm-hmm.
Now I'm going to put the double bond here. And now what I'm going to do is I'm going to put all of the hydrogens in. So do you see why I put hydrogens on those carbons, but not a hydrogen on that third carbon?
Right.
And now I'm going to put these hydrogens in. Now, for a Lewis structure, the one thing that's missing here are lone pairs. How do we know where to put lone pairs? And the answer is simple. We're going to put them in places where we need an octet. Can you see that there are octets everywhere except for oxygen and nitrogen?
Yeah.
So we're going to put a lone pair on oxygen and a lone pair on nitrogen. And there's your Lewis structure. Any questions on how to go from line to Lewis?
No.
Now let's look at Lewis and do the structural formula. So the structural formula is basically, not basically, it is the Lewis without showing the lone pair. The lone pair are there, we're just not showing them.
Okay.
So how many lone pairs are on this oxygen? The answer, 2. How many do we see? None.
Mm-hmm.
How many lone pairs are on that nitrogen? 1. How many do we see? None. They are implied. Now, the condensed formula, it's probably best to take the structural formula and turn it into the condensed. The condensed is a atom. So our first central atom is this carbon, followed by its terminal atoms. We show double bonds in the condensed formula. And then we show the next central atom and its terminals, the next central atom. And this one, I like to actually show the double bond like that.
Right.
And then, however, this is acceptable. These are both condensed formulas for that particular problem.
Okay.
Now, what's the molecular formula? Well, we count atoms. How many carbons? 1, 2, 3. How many hydrogens? 1, 2, 3, 4, 5. How many oxygens?
1.
How many nitrogens?
1.
And here, I'm going to actually use a little bit of whiteout here.
Oh, we put them in alphabetical order?
Yes. I guess whiteout is a brand. This says corrective tape.
Mm-hmm.
And so here's the molecular.
Jack. Oh, you can be on the table.
Okay, are you ready for the next one?
Yeah. Oi.
Okay, so for this one, you put the carbons in like so. Put the double bonds in. And put in that carbon, that oxygen, and you have to be careful because whenever you see something like this OH, the tendency is just to leave it that way, but you can't. You have to show the bond between the oxygen and the hydrogen, just like we showed the bond between the nitrogen and the hydrogen, okay?
Okay.
Now we have to add hydrogens to these carbons so that they can have 4 bonds each. And lone pairs. So this is the Lewis. What does the structural look like?
No lone pairs.
We don't show the lone pairs, right? So you should be able to do this for the exam. Take a line drawing and draw the Lewis, draw the structural. Whoops, I screwed up with the structural. I'm putting the lone pairs in. And, you know, a problem like this should be gravy. Okay, now what do you think? This is an interesting one. What do you think the condensed formula is? Well, do you see this guy here? The benzene ring?
Yeah, the C6H, not 6 though. I guess it's 6 because there's an extra H, but there's another C too.
It's C6H5.
Oh, okay.
Normally it's C6H6, and if it's H6, you know nothing's attached to it. But when you have an H5, it means one of the hydrogens is gone and something's attached to it.
Okay.
And so here we go. There's your condensed.
So
Now,
we put the oxygens before the hydrogen?
Yeah. Because here you write down the central atom, which is this carbon, right?
Mm-hmm.
And then you write down its terminals. Can you see this oxygen is terminal?
Yeah.
So, so that one is this one.
Mm-hmm.
And then you go to the next central atom, which is this oxygen, and its terminals.
So we could do O2H at the end too?
I don't like that as well, because when you write O2H, it makes it seem like the oxygens are similar, and they're clearly different, aren't they?
Mm-hmm.
This, in my opinion,
double bond on the top like we normally do?
You can. But this is something that you can write in a book, and you don't have to do anything special.
Right.
So the condensed formula was written so that you could write molecules out in a book and get an idea of how things were attached. Okay, what's the molecular formula? C what?
C6, oh, C7.
C7, H.
H6.
N.
C. No, no.
O.
O2H.
Nope, O2. We've already done all 1, 2, 3, 4, 5, 6 hydrogens.
Okay.
You only want to list the hydrogens once. You don't want to write C7H5 O2H.
Right.
You put all the hydrogens together. And that's a problem that people often have with getting the molecular, is a lot of times they'll leave the OH or an NH2, and you're not supposed to do that.
Mm-hmm.
Okay, let's see. How about this one here? So this is number 2 continued. Let's have a race and see who can come up with the answers for this one the quickest. On your mark, get set, go. Okay, I'm done.
I'm about to be done.
Good, I beat you.
Okay.
So do you have, let's look at your molecular compared to my molecular. I got C4H8O. Is that what you got?
Uh-huh.
Okay, and for the condensed, did you get one or the other of these?
I got the top one.
Okay. And for the Lewis, did you get the one here that I am pointing at?
Uh-huh.
And for the structural, did you get that?
Yeah.
Excellent. Okay, this one, on your mark, get set, go. I'm done.
Okay. I got C3H9N2.
All right. Now here's the condensed.
Yeah, mine's a lot longer than that.
Yours may look something like this. Something like that.
Yeah, I put CH3N and then I put CH3 with a 2 subscript.
Oh, well, if you're going to do that, why not put all three of them down?
I guess so.
That's just not right. It's like you're indecisive. I think it's got to be one or the other.
Okay.
And did you get these okay?
Yeah.
Excellent. Okay. So for these molecules, circle and identify the functional group. So here, I'm going to do that right here. I'm going to do this on the Lewis. So this is a ketone. And here, this is an amine. Now notice, I didn't circle all the carbons. I just circled one of them, but I could have circled them all, and that would be okay. Now here on the line drawing, I would circle all of that, and on the line drawing, I would circle all of that. How about on the previous ones? Well, I would circle this for the amide, or I would circle this. And here I would circle this, whoops, including the hydrogen for the carboxylic acid. And here I would circle this or all of this for the aromatic. And then what am I circling here? The alkene. So I'm circling them in both the line drawing and the Lewis because you want to be able to recognize them in either drawing, okay?
Okay.
Any questions about what I've circled for the functional groups and how they're named?
So this last one on the bottom next to the aromatic, is that Yeah, but that's also the carboxylic acid then. You're just showing it on the line drawing and the
Yeah.
Lewis structure. Okay.
Yeah, so that's the carboxylic acid. This is the amide here and here, and this is the aromatic.
Mm-hmm.
And here, this is the ketone. There's no Y in ketone. Okay, for the molecules in problem 2, draw one structural isomer of each. Now, what are we going to do about this guy? We've got to keep the same number of atoms. And I got to tell you, when you have a double bonded oxygen, it's really, oops, I'm starting off with a different one here than, but at any rate, when you have a double bonded oxygen, you want to keep the double bonded oxygen. It's hard to get rid of. So what are we going to do? I'm going to move this over to this valley. Is that a structural isomer?
Yeah.
No, it's not. Because this is 2-butanone.
Oh yeah, it's the same thing.
And this is 2-butanone. And in fact, we don't even need the 2. Because for a butanone, it has to be on carbon. Well, it can't be on carbon 1 or the last carbon. Now, what if I did this? Would this have the same number of carbons?
Yeah.
Now, we found this formula to be C4H8O, right?
Yes.
So this is C4. How many hydrogens are on this guy? How many here that I'm pointing at?
3.
And how many next to that?
2.
Grand total of 5. How many here?
2 and
Grand total of 7. And how many here?
1 for 8.
For 8. Okay, that's looking good. And how many oxygens?
1.
Now, some people draw this way. I don't. I draw it this way. And the reason I do that is a lot of people miss that hydrogen, so I put it there. These are the same.
Mm-hmm.
Okay, so we have a structural isomer. Oh, and now we're supposed to also, for number 5, we're supposed to identify the functional group. So what is that functional group?
With the OH.
That's not an OH.
The OCH. With the double bond is the, I want to say, it's actually not. It's the aldehyde.
That's correct. So when it's not an OH, but it's just an H, it's an aldehyde. Okay, so what about this guy here? Let's go ahead and do this guy now. What are we going to do for a structural isomer of this guy?
I'm going to draw it out so I can see it better. Can we put it on carbon 3, the oxygen?
Over here?
No, on the carbon that's connected to the NH.
This one right here?
No, the next one.
This one. Like this?
No, because didn't you say we want to keep the double bond?
Usually you do, but you know, we've got to work with this, so let's find out if we need to. Here we don't have a double bond, so we have to put an H here, right?
Right.
Are these isomers? Well, this one, we said that the formula was C3H5NO, right? Is this C3?
Yeah.
How many hydrogens? How many here?
2.
How many here?
3.
1.
Oh, and then we'd put the lone pairs on. I think.
Yeah, because it's got lone pairs, right?
Yeah.
So there's only 1. So we got 2 plus 1 is 3.
Plus 2.
Oh, you were giving me a total, weren't you? Now, how many there?
2.
So plus 5, 7. Oops, that's not going to work.
Okay.
What else could we try? What if we did this? See, we have 2 double bonds here, right?
Yeah.
I think we want another double bond. What if we put a double bond to the nitrogen? So how many carbons in this one?
3.
Okay. How many hydrogens?
1, 2, 3, 4, 5.
How many nitrogens?
1.
How many oxygens?
1.
Okay, the functional groups. What do we call a carbon bonded to a nitrogen?
An amine.
A carbon bonded to an OH.
An carboxylic? No. Yeah. Oh, with the double, it's the carboxylic.
Yeah. We need a double bond to an oxygen to make it a carboxylic acid. This is not to an oxygen, it's to a carbon. So carbon double bonded to a carbon?
An alkene.
There we go. I'm wondering if we could have done something like this. How many carbons do you see in this?
3.
Okay. How many hydrogens?
1, 2, 3, 4, 5.
How many nitrogens? I'm sorry.
1 and 1 for nitrogen and oxygen.
Oh, so this is also a structural isomer. And what would you call this guy?
Oh, and the NH is the amide.
Correct. So you see, we could have gotten rid of the double bond and put a ring in instead and accomplish the same formula.
Mm-hmm.
That's why the formula for alkenes is CnH2n, and for cycloalkanes, excuse me, for alkenes, CN blah, blah, blah.
It's the CnH2.
Better if I write it out.
Yeah.
This is for alkenes and for cycloalkanes. So you see how we could have used that knowledge and said, well, hey, let's make a ring.
Right. It's easier too.
Yeah, it's probably easier too. Okay, let's see. We have one more to do, I think. Oh, 2 more to do. So how about this guy? Probably the easiest thing is to do this. We had this as C3H9N. How many carbons here?
3.
How many hydrogens? 3
2,
plus
4.
2 plus 2 is 7 plus 2 is 9. And what are we going to call that guy?
The amide.
Amine.
Because of the
We
single
could've-
bond.
Yeah, we could have also done this. And again, this is an amine. And the last one, I'm not sure what we're going to do. This one might be a challenge. I don't know if we can come up with any structural isomers. But it was C6H6O2.
For the molecular?
My bad, C7H6O2. Okay, you got any thoughts on this one?
Well, could we change the cyclic one to 6?
We could certainly try that.
That's what I would start with.
Or
we could make it, could we try to make it a pentane instead with a methyl?
you mean like this? Pentane with a methyl?
Yeah.
Okay, we could try that. How many double bonds do you want to put inside of here? What if we put one here, and one there? Because we had 3 here. Wouldn't it be nice to have 3 over here?
Right.
Okay, let's see what the formula is. Do we have 7 carbons?
One, 2, 3, 4, 5, 6, 7.
We do. How many hydrogens do we have? 1, 2,
3,
4,
5,
5,
6.
6. Ooh. How many oxygens? 2.
2.
Boom. What do we call that?
The carboxylic
acid. What do we call that?
The alkene.
What do we call that?
An alkene as well.
And what do we call that?
An alkene.
Right, we've got 3 alkenes here now, whereas this is an aromatic. Boom. Pretty good. Now, what you don't know, well, never mind. I'm not going to tell you. Okay, so we did 4 and 5. How about 6? C7H16. Line drawings for the 5 isomers that have a parent chain of 5 carbons. So how do we do this? Well, we start with 5 carbons. And it says there are 5 of them, right?
Yeah. I think that's what you said.
Okay, 5 isomers. So there's 1, there's 2, there's 3, there's 4, and there's 5. And when I say there's 5, there are the 5 parent chains.
Mm-hmm.
So now we have to take 2 more carbons and put them on this sucker.
So put 2 on carbon 1.
Okay, no. Carbon 1 is this
carbon
one.
2, I mean.
Okay. So what are you going to call that? This is number 7 also.
2,2-dimethyl pentane.
Yes, excellent. Now what are you going to do?
keep it one of the methyls on carbon 2 and move the other one to carbon 3.
So this is 2,3-dimethyl pentane. Now what do you want to do?
Move both of them to carbon 3.
You sure you want to do that right now?
Move one of them to carbon 3 and have one on carbon 4 and 2.
Okay, so keep one on 2 because that's what we've been doing so far. And move one of them around.
So 2,4-dimethyl pentane.
Okay, now maybe we can move them both over.
3,3-dimethyl pentane.
Okay, now we could keep one on carbon and 3 and move the other one to carbon 4 and have a 3,4, right?
Right.
You're supposed to say no.
Oh, because it's the same as 2,3.
It is a 2,3. So what else are we going to do? There's one more.
Put an ethyl.
Where?
One, two, three, four, five. 1, 2, 3, 4, 5. On carbon 3.
Okay. So we have a nice river meandering out from between the mountains. And what are you going to call this one?
3-ethyl pentane.
Ethyl pentane. I'm not going to bother putting a 3. Why is that?
Because it wouldn't be a pentane if you put it on any of the others.
That's right. So there's 6 and 7. We've found the 5 and we named them. Now, 8. Lactones are cyclic esters that can be hydrolyzed with water. Draw the hydrolysis product of the following lactones. So this is a lactone. Now, do you remember how we hydrolyze these esters? You add water, and where do we break it? Always right here between the carbonyl and the oxygen. And we always add an OH to the carbonyl and an H to the oxygen. And here's how you break it. So first thing you do is find the carbonyl. The carbonyl is the carbon double bond to the oxygen. And then you break the bond between the carbonyl and the singly bonded oxygen. And then you add OH to the carbonyl carbon. And you add H to the other oxygen. So do you kind of understand those directions?
Yeah.
Okay, so let's do that for this next guy. Tell me when you have your product.
Okay, so I see where I'm gonna break it. Add OH. Okay, I think I have it.
So you're gonna break it right here.
Right.
There's the oxygen. And we're going to add an OH to the carbonyl and an H to the oxygen. That's it. What are the functional groups in these two products? Carboxylic acid and alcohol. Carboxylic acid and alcohol. Okay, let's try this one, only I want you to draw it this way, okay? So you see how the house, I'm putting the oxygen on the right-hand side instead of the left?
Yeah.
I want you to draw it that way. And just so that you get the idea that the oxygen doesn't have to be on the left. Fair enough?
Right.
Okay, draw the product.
Okay.
Okay, so this is what I get. I'm going to add the OH here and the H there. Did you get something similar?
Yep.
Excellent. Now I want you to draw the next one like this. We're drawing it upside down, so to speak. Sounds like you live near an airport.
I have my door open. It's just cars passing by.
Oh.
Is it annoying? Should I shut it?
No, it just sounds like you live at an airport. I was thinking I would hate to live near an airport.
No, but I live close to a pretty busy street. At least busy enough to hear cars.
Yeah, I live close to a busy street too.
I'm gonna flip it right side up.
Why not just do that?
Some reason I'm missing something. Oh, well, then I'm not missing something.
Okay, so what do you add to the carbonyl?
You add an H at the end of the O and an OH.
Now, does it matter if I put the H on the left or the right?
No. Well,
No.
yes, because you want to bond the oxygen.
This is still an alcohol, whether I put the H on the left or the right.
Okay.
Now here, do I want to put the HO or can I put an OH?
You want the O closest because the H will be terminal to the O.
Exactly. So here you see it doesn't matter, but here it does.
Okay. So the order matters on the carbonyl.
So this was not asked in this problem, but I'm going to give you another problem. Are you ready?
Yeah.
Those other molecules that are called cyclic esters are called lactones. This is a cyclic amide called a lactam. They can be hydrolyzed with water. Take a guess as to the product. Go ahead and put yourself on a limb, draw it. You don't need to show it to me. And when you're done, let me know.
Okay, I'm done.
Excellent. So guess what? You're going to break it between the carbonyl carbon and the nitrogen instead of the oxygen.
You're right.
And then I'm going to draw this. And I'm still going to put the OH on the carbon with the carbonyl, and the H is going to go on the nitrogen. Is that what you got?
I only accounted for one H on the nitrogen instead of two.
But there was already one H there. So
Mhm.
you have to add another one,
Okay,
because otherwise you would only have one bond to nitrogen and another bond to nitrogen and 2 bonds total.
right.
And we know nitrogen makes 3 bonds, right?
Mhm.
So remember, when you add water, you need to account for both the H and the OH. And there's the OH, and there's the H. Fair enough?
Yep.
Okay. Let's take a look at number 9. For the first lactone, write a balanced reaction with O2. So the first lactone was this guy, plus O2. What is that going to make?
For the combustion, CO2 and H2O.
Okay. Now this lactone is C what?
C2.
H.
1, 2, 3, 4. That's it.
I see 2.
I'm putting 2 off of the carbon and then 2 off of the oxygen.
Oh, does oxygen make 4 bonds?
Oh, no.
So isn't this the Lewis for that one?
Right, okay.
So C2H2.
O2.
Okay. How many CO2s will we make?
At least 2.
Okay. How many H2Os will we make?
At least 2.
I think since there's 2 hydrogens, we're going to make 1.
Oh, I forgot about the other oxygens.
Well, we'll worry about those last.
Okay.
So we have the right number of carbons, the right number of hydrogens. How many oxygens do we see on the left?
4.
How many do we see on the right?
3.
Oh, okay. This is going to be tough. What if we double everything? Do you think that might help?
Maybe triple.
Triple? Maybe triple, because we do have an odd number here, right?
Well, because it's 4 and 3, so I don't know.
I don't know either. I haven't tried to balance this one before.
Okay, C2H2.
It may be impossible.
Maybe hope to write it down.
I'm going to double everything to see what happens. And see if I can work with that. So now I have, no, that still doesn't work. You know what I'm going to do? Carbons 2, hydrogens 2, oxygens here we have 5, right?
Mm-hmm.
Oxygens here we have 2, and here we would like to have 3, wouldn't we?
Right.
But we have 2. How can we get 3 oxygens there? I know, I'm going to put 3 halves.
3 halves, yeah.
Now, we don't like coefficients of halves, so let's double everything. And let's count. 4 carbons on the left, 4 on the right. 4 hydrogens on the left, 4 on the right. 4 oxygens here plus 6 more here for 10 oxygens. 8 oxygens here, 2 there for 10. Boom, we got it. What do you think? So we want to kind of leave oxygen for the last thing to balance and just figure out what number there is going to work. The thing that made this tricky is that there were 2 oxygens here already.
Right.
But you see how kind of I worked it out right there?
Yeah, it makes sense.
Okay. The molecule 2,3-dichlorobutane can be produced from the reaction of 2 different alkenes with Cl2. Write out each reaction using line drawings and distinguish between the alkenes. So do you see that the product of 2,3-dichlorobutane looks like this? 2, 3. Or we could write this. For a condensed drawing. So we're going to add chlorine to some sort of alkene. Where should the double bond be?
Between the 2 chlorines?
So are you saying they should be right here?
Yes.
And that would make that?
Alkene.
This alkene plus that chlorine would make this
alkane.
We call it a haloalkane because it's got halogens on it.
Right. Or the alkyl halide.
Or an alkyl halide, that's right.
Alkyl. Is it alkyl or alco?
Alkyl.
With a Y?
Yeah, like you're trying to say I'm going to kill someone. Alkyl. Alkyl.
Okay.
Or haloalkane, which is much easier to say.
So we should also know that the haloalkides, when they react with a
hang on a second.
Halogenated,
Just call it.
It's the same as the alkane.
You called it an haloalkane. Because you must play that game, Halo, huh?
No, I don't play video games.
Oh. I know there's a video game called Halo, but
there is.
Okay, so what else could make the same thing? It's got to have a double bond between carbon 2 and carbon 3.
So what should I be thinking about right now?
The answer?
I don't know. I'm at a loss right now.
Well, is there anything interesting about alkenes that you don't see in other molecules?
The double bond?
Yes, the double bond. And what can the double bond result in?
Oh, we're going to come up with the cis version of this.
Okay, so would this be the cis version?
Yeah.
So how do we distinguish between these? What would the name of this guy be? Trans 2-butene, right?
Right.
And what would this guy be?
Cis 2-butene.
And they both would result in these molecules, correct?
Right, okay.
Okay, it's 2 different alkenes. Are these different alkenes?
Yeah.
Yep.
Absolutely. Okay, I always forget about the cis ones.
Yeah, so that's something that should be in the back of your mind all the time when you're dealing with alkenes is think cis trans.
Right. And when we're doing the cyclic ones, it's the meta, para, and ortho?
No, not with the cyclic, with benzene.
Oh, just with benzenes.
Yeah, here you have ortho, meta, para. The cyclic ones, they're not orthometapara, but with the cyclic ones, you can have cis and you can have trans.
So are benzenes all cyclic hexanes or hexenes?
They're not hexenes. They're actually it's a very well. You don't really want to call it a cyclohexane. It's not, and it's not a cyclohexane with 3 triple bonds. Because here's the deal. If you had this 6 carbons, right?
Yeah.
And 3 double bonds, and you added bromine to this, and let's call it XS, and you don't need light with alkenes, this is what you would get. You'd put a bromine here and a bromine here where that double bond is, a bromine here and a bromine here where that double bond is, and a bromine here and a bromine here where that double bond is. That's what would happen with this. Now, if you put this in and you add bromine excess, what would happen here is no reaction. So what does that tell you about this molecule compared to the one above? It's stable.
Right.
So there's something special about having that extra bond there, which makes these 6 electrons not stuck between 2 carbons like they are here. These 6 electrons are actually able to occupy a space above and below the plane of carbons and delocalize, and that means spread out, so that they're really stable. I mean, you've got 6 electrons here, you've got 2 electrons stuck right between 2 carbons, and those electrons don't like each other. Here, you've got the same 6 electrons that are up here, but they're spread out all over both carbons, or all 6 carbons, nice and evenly. What could be more beautiful? So this is a highly, highly stable molecule. And that makes it a problem, because when you make this molecule and it goes out into nature, it doesn't go away. And it causes problems. It causes problems because it's a flat molecule, and it can fit into other places where you have molecules. For people, one of the big problems with this would be that it would actually fit into DNA very well. Okay. But it doesn't belong there. So it could upset things.
And that's just because it's planar?
Because it's plain, it's completely flat, and it actually fits in with other flat things in DNA very well. And that's a problem.
Where do you get exposed to benzenes?
Usually places of industrial import, like refineries, things like that. It's a common byproduct of refining fuel. Okay. Or oil. Mm-hmm. Okay, so that would be the answer to number 10. So we just went through the whole homework, and what you did not know I was using you for was to make a video that shows the answers to the homework. So thank you for letting me do that. I appreciate it.
Well, now everyone can hear me.
Fantastic. If they've been listening to the videos, they've heard you before.
Oh, I don't care.
Excellent. Thank you for your help. I really appreciate it.
No problem. It was really helpful for me.
So I imagine you are doing your report on the carbonate, right?
Yeah.
Okay. Now, also, I don't know if you want to play with it, but if you use Word, there's this thing that you can insert an equation. Mm-hmm. And it's really great for writing out chemical reactions, for writing calculations. You don't need to use that for writing out the calculations. You can print your report and pen in your calculations by hand because they're kind of hard to do
Right.
unless you know how to use equation editor. But equation editor is fantastic. It's how I make things for you guys to read, and it works pretty well, and it doesn't take very long to learn.
I've used it a few times.
Yeah, you can give it a go if you want. You don't have to, but it's pretty cool. And who knows, maybe somewhere down the line, you put that down on a resume. I know how to use equation editor to write out calculations.
Right.
That's a skill most people don't have.
Good to know how to use Excel that way too.
I know Excel is very powerful. I've just never been good at it.
Yeah.
Because I don't use it. And
Yeah.
I don't use it because I don't need to.
I only know how to do a couple things.
All righty.
Cool for trends.
Pardon me?
It's cool for like analyzing trends.
Yeah, I know it's great for making graphs, and you can do all sorts of things like bar graphs. You can even do other things like a linear graph and get an equation, but I just haven't mastered it. And being an old dog, I never will. All righty. Hopefully we'll see you later this week.
All right. Thank you, Tony. Have a good night.
You too. Bye-bye.
Bye.